Okay, so be just a continuation of your previous notes, because last time we talked about covalent bonding, we talked about this idea of formal charges. We we probably did uh, and we're ready to move on from there. But guys, today what we're going to do is we're going to talk about some of the things, again, that we couldn't talk about last year relative to covalent bonding. So last year, you guys were drawing Lewis dot structures. You came up with two structures that were different, but they both worked. And I lied to you and I said the one that is symmetrical is the one that's right. And now you guys understand that it's way more nuanced than that. First of all, there is no such thing as right. What is the word that we use instead? Preferred or tends to. Guys, you always want to use vague terms, right? Because the minute I learned this fighting with my wife, have I shared this with you? My wife is good. And so if I ever go to my wife and go, you always do this, all she's got to do is come up with one example of when she didn't, and now I'm wrong, right? So when you get married and fight with your spouse, never say always or never, because all they got to do is find one example where that's not true and you are universally wrong. That's my little, never mind. Yeah, we tend, honey, you tend to, you prefer. Then she's going to know you're working her, and then she's really going to get mad. But guys, in a similar fashion today, off. So guys, what you're going to find out today, and this is all about resonance structures, because what you're going to find out today is sort of the opposite of what you found out previously. So previously, relative to formal charges, we said there are multiple ways of drawing structures, but one is preferred. Well, guys, today what we're going to do is sort of talk about the opposite. We're going to talk about structures where one's not enough. And we're going to talk about resonance. This is pretty cool. You'll see. So guys, do this for me. Draw the Lewis dot structure for ozone. Ozone is O3. It's this interesting, simple molecule that exists in our upper atmosphere. And it's actually like the opposite of a greenhouse gas. Instead of trapping heat, it actually keeps the radiation from getting in the first place. And it functions as sort of like sunscreen for the earth. And then we found out in the 1970s that we had a big old hole in our ozone layer up above the North Pole. And we figured out that the reason that that was there is because chlorine atoms actually have an amazing ability to rip ozone apart. And as our Earth spins and our atmosphere churns, all of the chlorine gas that we were releasing into our atmosphere was going to the North Pole and ripping ozone apart. And to our credit, we fixed it. The ozone hole's not there anymore. Because frankly, we changed the propellant in hairspray and changed the refrigerant in air conditioners, because both of those things contained a lot of chlorine. They were called CFCs, chlorofluorocarbons. And we got rid of them, and now we fixed it, and it's all better. Have I babbled long enough that you guys are done with the Lewis dot structure? So guys, what'd you come up with? Just in broad brushstrokes, describe to me what this molecule looks like. Thank you, Mark. Wait, yes, thank you. That is plenty broad. All right. Good night. All right, so let me draw it then. So 14 electrons, is that right? So we got to get 14 on there. So if we spread them out, we've got 2, 4, 6, 8, 10, 12, 14, like so. Is that right? So then we end up in this spot where one of these oxygen atoms doesn't fulfill the octet rule. And how do we resolve that situation? We create a double bond and we take off 2 of these electrons and we go like that, and that would then be the Lewis dot structure for ozone. Is that okay? Okay, and I suspect that some of you are going, wait a second, he's messing with us in the same way that I messed with you with carbon dioxide last time. Remember how I purposefully gave you carbon dioxide and I drew this to mess with you? Because I'm not doing that now. This is actually what ozone, well, this is what we believe ozone looks like, but it's actually wrong. This is not what ozone looks like. And so let's talk about how we know by drawing. And guys, this is not trivial. This is important. This is the stuff that we skipped at the end of last time. Remember that there was that slide of notes and I said, just read it? Well, guys, this is one of the things that you needed to pick up on. It goes like this. So, guys, we've got a single bond here and we've got a double bond there. Which one is stronger, single or double? Why is a double bond stronger? More sharing. And the way that we would describe that is we would say that this has got a larger region of increased electron density. And literally, guys, what you're going to find out, don't write this down, but literally what you've got for a double bond, let me just get this out of the way. Literally what you've got is this. You've got one region of increased electron density that's in the bond axis, and then you've got another region of increased electron density that actually is above and that's outside, it's above and below the bond axis. So you really have 2 where we count this as 1 and then we count both of those as 2. But literally you've got 2 regions of increased electron density, and therefore that makes that bond stronger. We'll talk more about this later. But guys, for now, you just got to understand that the double bond is stronger than the single bond. Is that okay? Okay. So guys, if the double bond is stronger, will it be longer or shorter? Shorter. So guys, are we clear on that? Single bonds are longer and weaker than double bonds. Double bonds are stronger and shorter. Is that okay? Okay. Now guys, let's look at this, because it turns out this is actually the structure of ozone. Well, be careful. This is getting closer to the structure of ozone because we've got 3 domains around the central oxygen. So it's not linear. What is that shape? Bent, and it's got a trigonal planar domain geometry. But guys, here's the thing that's interesting about this, and this is the part that we need to explain today. If you measure the lengths of the bonds in ozone, it turns out that this one is 1.278 angstroms long. You don't need to know that, but it's 1.278 angstroms long. Guess what this one is? It's actually the same. We would expect this to be shorter, right? Because we would expect this double bond to be shorter than this single bond. But guys, it turns out in ozone, the bond lengths are exactly the same. So what does that tell us? Yeah, this is not the bonding that exists in ozone. So guys, let's talk about the bonding that exists in ozone. So write this down with me. Here's the way this goes. Draw yourself an oxygen, draw your unbonded electron pairs, then you've got an oxygen here, then you've got an oxygen here. But then guys, this is where this gets a little bit weird, because what you actually end up with, and guys, do not ever write down or say these words out loud, but guys, what you actually end up with is a 1.5 bond existing in both places simultaneously. So guys, the first question that we need to ask is this. How did you know that this would be the case? So guys, let me go back here and show you how we know. So I frankly don't know how to do this. I think if I go up, that'll go away. And then if I do this, no. Oh gosh, I'm not clicking at all. Okay, let me see if I can do it this way. Yeah, that worked. Why did that? Okay, there we go. So guys, when we originally drew the Lewis dot structure for oxygen, did any of you have your double bond on the left? Some of you did, right? But guys, some of us had our double bond on the right. Some of us had our double bond on the left. Which one's correct? They're the same. And guys, that's how you know that this 1.5 bond reality happens. Because what happens is as you're drawing the structure for this thing, that double bond could be in either location. And that's when this 1.5 bonding takes place. When you're drawing the Lewis dot structures, if you get to the place where there could be a double bond in more than one location, and those locations are equivalent, guys, what actually ends up happening is this, and you end up with that double bond existing partially in both places simultaneously. Okay, go ahead. Well, and that's actually, I'm going to touch on it now, but when we talk about hybridization in Unit 9, we're going to do a much deeper dive on this. But the reason is this. I'm going to probably say more than I should, but let me just do it. So when these bonds form, wait for a second. I may be able to just show you. I don't remember if our book gives us a graphical representation of this one. It really doesn't. Levi, let's do this. Let's table that question for a minute, and then we're going to do another one of these, and then I can show you for sure. Is that okay? Go ahead. No, and that's and those are the kind of questions that we need to be asking. And if you didn't see Jessica's hand, she's talking about this idea of it doesn't know which side to be on, and it's like choosing. You're like flipping back and forth. And that is not what's happening. It's not like left, right, left, right, left, right. It's actually in both simultaneously. And Levi is trying to picture this, and I'll show you a picture of it in a minute. But let's do this. Let's talk about how we represent it and how we talk about it, and then we'll do another one of them, and we'll do nitrate. And then when we do nitrate, I'll be able to show you a better picture, and I think it'll make more sense. Go ahead, Mark. No, this is, so, I mean, the answer is yes, because those are the same. So if you measure the bond length in a single ozone molecule, or if you do it to a bunch of ozone molecules, you'll get exactly the same answer. Your standard deviation is close to none. They don't deviate. They're really this. They're not in between. It's literally this. And it's not like they're growing, you know, like Jessica was doing. It's not like they're growing and shrinking. They're this. And so guys, maybe we should talk about this. This number back here, this one, well, how can I do this? Clear this, do this, do this, do this, do this. Guys, this number 1.278, how do you think that compares to the length of a single bond or a double bond? It's actually in between. So this number is actually shorter than a single bond, but longer than a double bond. It's actually in between the two. Does that make sense? Okay, so then guys, the question becomes this. How do we talk about this? How do we represent this? And guys, you got to be really careful about this. You already know, don't say 1.5 bond. But guys, in addition to that, you will also never draw that. Never draw 1.5 bonds. So guys, how do we represent this? And the answer is like this. So guys, when you're representing this idea of this bond exists, this double bond existing in more than one place simultaneously, you actually draw it like this. And do this in your notes, guys, this is important. You draw both of these structures. So guys, let's talk about what you're looking at. So these are the two different structures for ozone. Now, which one of these is correct? Both, but neither, right? It's actually an average of the two. And guys, this is the way that we draw this. You draw a double-headed arrow between the two. Now guys, you ready for super nitpicky? Do not draw that arrow, because what does that arrow represent? Equilibrium. And it's not the same. It is literally a double-headed arrow like that. They actually care about that, which makes me grumpy. But it's not the equilibrium arrow, it's the other. Wow. That's not better. I have no idea what's going on, but it's kind of fun. So, go ahead. Did you ever have like the 1/3 bond? Yes, and we're about to look at that. But you'll never call it that, right? And guys, in a minute we're going to talk about the terminology that we use to describe this. But guys, this then is the idea. These two structures are equivalent except for the placement of the electrons. Here are the double bonds on the right, here it's on the left. So guys, the Lewis dot structure for ozone is the average of these. We represent this by including both conformations. Guys, this is actually a word that you need to know. One of the words that we will use to describe this is conformations. And then you put a double-headed arrow between them to describe, to show that they both exist partially simultaneously. And guys, again, as Jessica got us thinking, these things do not isolate or oscillate. They truly are an average of both. And guys, your book shares this thing about a paint analogy, that red and blue make green, but that doesn't mean it's shifting between red and blue. It's literally when you mix them together, you get a new color. The same thing is true here, but here we get a new bond length. Is there a reason why we represent it like that? I feel like logically it makes more sense instead of saying this color is blue plus red. Right. Yeah, and I understand what you're saying, but so Luke is saying, in the same way that we don't describe green as showing the yellow and the blue, that's right, yellow and blue make green, isn't it? Or whatever, purple. So, but with that said, why don't we just draw them both like that? And the answer is because when we do, we can't then accurately describe the bonding that's actually taking place. And you'll see what that means in a minute, because I'm going to show you some other images, and I think you'll go, okay, I see it now. Because when you look at the actual bonding, it gets a little scattered if you represent them in one big pile. So guys, this is the agreed upon way to represent these. Okay, so are you all caught up? Are you okay? So guys, what we need to do then is we need to talk about how we are and how we are not going to talk about this. Hey, how are you? Can you get it? Thank you. Let me come out with you. Hey, are you, oh. Yeah, that'll be fine, thanks. We have the best special ed department in the whole state. I love it. Okay, so guys, you good there? Are we all okay? So guys, then the question is, how are we going to talk about this? So let's talk about how we're going to talk about this. So guys, these are the terms that you need to use when you're describing this phenomenon. So guys, the first term is resonance stabilized molecule. What you're going to find out later in the year is that this phenomenon where this double bond exists partially in multiple directions makes molecules more stable. So this multiple bonds in multiple direction stuff we call resonance. So ozone is a resonance stabilized molecule. That's one of the terms you need to know. The next one are conformations. Remember we underlined that previously. So the conformations are the individual structures that make up the average, which is what the molecule actually looks like. Guys, the third term that you need to know are what are called resonance structures. Those are the same as conformations. You can use those interchangeably. And then guys, this last term is not going to make any sense to you until we talk about hybridization. But these partial bonds, right? The things that we represented with the dotted line that you promised me you would never draw. Guys, those dotted lines actually have a name, and they are called delocalized pi bonds. And that will make a lot more sense to you when we go over hybridization. Yeah, right. Guys, this is all some of this is chapter 9. So guys, those are the do's. Here are the don'ts. Guys, never, ever, ever talk about 1.5 bonds. If an AP grader sees 1.5 bond, they're just going to keep reading your next answer and just give up on you. Do not call these things 1.5 bonds. Also, do not talk about resonance bonding. That is not a thing. So guys, let's use ozone as our example, and let's talk about how to talk about this intelligently. So guys, what we would say is ozone is a resonance stabilized molecule. It has 2 conformations or resonance structures. And then we could also say that ozone has 2 bonds that contain or utilize delocalized pi bonding. So guys, those again, don't draw this, but these bonds that we represent like this, these are delocalized pi bonds. We're going to talk more about that when we look at another example in just a moment. But these are the terms to use. But guys, do not call this resonance bonding. This is delocalized pi bonding, and these are not 1.5 bonds. And this is what's called a resonance structure or a conformation, and ozone is a resonance stabilized molecule. Is that okay? You get the idea? Okay. So guys, with that said, let's do this. Let's play this game again, if I can do this. And then let's try this. Let's do nitrate. Guys, draw the Lewis dot structure for nitrate. NO3 minus 1. Okay, I'm curious. I gotta go see what that is. It's the paper bucket. Guys, Guys, if you understand what you're doing, this should take you a while. So, guys, while you're wrapping this, something's burning. I'm going to go wash my hands really quick. So, guys, allow me to at least get us started. Maybe you were really feeling brave and you drew it trigonal planar. But guys, you got to this point where you realized you're going to need a double bond in order to complete the octet for nitrogen. And then you're like, wait, there's 3 different places I could put that. So where do you put it? All 3. So guys, what you end up doing, and I'll move this down a little just so I can get things to line up a little better. Guys, what you end up doing then is this, and, oops. And so here, we'll go like this, and then we can go similarly. And guys, in a second, I'll share with you a common mistake people make. Like so. So guys, if I had just turned you loose on this and said everybody draw 1, we could have got any one of these 3 structures because these nitrogen-oxygen bonds are all equivalent. Because they're all equivalent, that double bond could exist in any of those 3 places. So what it does is it actually exists in all 3 places simultaneously. So we separate them like this. Luke, here's about to come another answer to your question about why do we draw them like this. Guys, a very, very common mistake that people make is this. You got to be careful where you put your electrons. I will see this frequently where people just start dumping electrons on the board and you end up with too many electrons on one of your atoms because you're just dumping electrons on the paper and you're just surrounding all your oxygens with electrons. Realize the oxygen that's got the double bond can only have 2 unpaired electrons, right? So Luke, to show you the example then, if you look at this, if you were to draw oxygens with the partial bonds, then what do you do with the other electrons? Because that wouldn't be right because it's too many, and this wouldn't be right because it's too few. So there's no way to satisfy octets correctly, if you will, if you draw it the other way. Does that make sense? Okay, so guys, let's then apply our words to this. So what do we now know about nitrate? It's a resonance stabilized molecule. It has 3 conformations or resonance structures. And then, guys, it contains this thing called delocalized pi bonding. Now guys, before we look at what delocalized pi bonding looks like, let's talk about this idea of resonance stabilized. Guys, what do you know about nitrate from the summer and the very beginning of the year? All nitrates dissolve in water. You want to know why? Because nitrate is a resonance stabilized molecule. When nitrate dissolves into water, it resonates. It doesn't when it's bonded to a positive ion. When you've got nitrate bonded to a positive ion, it doesn't, but when it carries off into solution, it takes on this resonance stabilized form, which makes it stable on its own, so it doesn't need to go back to the metal from which it got its electron and try to reform into the salt. Guys, this is actually part of the reason why all nitrate salts all dissolve in water. Guys, what other what other anion also always creates soluble salts? Acetate. And guess what? Acetate resonates as well. Oh gosh, thank you. Yes. How am I doing? Not so good. Yeah, yes. Thank you for mentioning. Yeah, because this is an ion, it should be. No, that. So here, so we've got, so that's 5, 18, and 1 is 24. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Are we okay? You guys good? So now, guys, let's do this. What does this delocalized pi bonding look like? So guys, grab your 10. So guys, on page 310, you'll notice that we've got the 3 conformations of nitrate, right? You guys good on that? Because guys, that's what we've already got on the board. The question is, what does this delocalized pi bonding actually look like? Guys, go back to page 356. So on page 356, sample exercise 9.7, you'll notice that they've given you the 3 resonance structures or conformations for nitrate. But then guys, look off to the left. The top thing that you're looking at there is actually what nitrate would look like if that double bond existed in one place. So, guys, I'm sorry I don't have a thing to project, but this is the idea. So somebody was asking about this idea of kind of what these bonds look like. So guys, the black lines represent what you're going to find out later are called sigma bonds. They are bonds that exist within the bond axis. But then guys, these pink lobes represent that other region of increased electron density that is outside of the bond axis. So the idea is that if nitrate was only single bond, double bond, this is what it would look like, and that double bond would be shorter because of that second region that's represented by the pink lobes. But guys, that is not what happens in nitrate. Nitrate actually looks like the bottom guy, and what happens is those p orbitals wrap all the way around the molecule in all 3 directions simultaneously, and those pink lobes above and below the plane of the molecule are actually what a delocalized pi bond looks like. Yeah? So Yes, but. So it is a new orbital, but it is a molecular orbital, and we're never going to talk about that. So the way that we're going to talk about it, and we need to do this when we do hybridization, but the way that we're going to talk about it is this. If you look at a nitrate molecule, and if you look at the S and P orbitals, what you'll find out, this is going to be horrible, what you're going to find out is that each one of these molecules has a p orbital on it that is half full. And what ends up happening is these p orbitals, and remember, p orbitals look like this. So the p orbitals are like figure eights, right? And what happens is those p orbitals actually all end up wrapping together above and below. And that's what they're showing to you. Maybe if you look, yeah, actually it's not bad. So if you look at that picture on 356, they show you these p orbitals. But they don't just wrap together nitrogen to one oxygen, they wrap together completely nitrogen to all three oxygens above and nitrogen to all three oxygens below. And that's what we call delocalized pi bonding. For that to completely come together, we've got to talk about hybridization, but that's the basic idea. That's correct. So, right, so an electron from nitrogen, an electron from each of the oxygens, all smear together above and below. Yeah, go ahead, Susan. That's correct. And again, we need to talk about hybridization for this to fully make sense. But take, for example, carbon dioxide. I mean, really, to answer this, I'm going to have to teach you about you know, a carbon dioxide could be distracting. Let's do this. Take, for example, CH2O. So this molecule actually looks, it actually looks like that. So that's CH2O. So the question is, how does this work? And the way that this works is when the carbon bonds to the oxygen, it creates a single bond. Then you've got one p orbital that exists on both the carbon and the oxygen, and this wraps together top and bottom, and that creates the second bond of the double bond. So in this case, this doesn't resonate because these locations are not equivalent to that location. So you literally have a double bond and then two single bonds, and the double bond is created by this additional overlap of these P's. In something like nitrate, you've got the same idea, but now you've got these p orbitals, and these things are equivalent to each other, so they wrap around in all three directions simultaneously. So a true single bond does wrap like this. A delocalized pi bond wraps in multiple directions at the same time. Did I say single bond? I meant double bond. I'm sorry. So in a true double bond, they wrap in one direction and it's fixed. In this delocalized pi bonding, those p orbitals wrap in multiple directions at the same time. Right. And that's actually what they're showing you over on page 357. That picture in Chemistry of Vision, you see how they have those two P's that are touching each other? That's actually what a pi bond looks like. It's two p orbitals. That's what I'm trying to draw for you here, are these two p orbitals literally creating a new region of increased electron density, where in a delocalized pi bond, they go multiple directions at once. We need to talk. we need to talk about hybridization. When we talk about hybridization, this will make much. Plus, are we all right? Okay, so guys, with that said, are we good on these ideas about the things we are and are not going to talk about? Okay, so guys, we're actually ready to wrap up the day and you're going to get your homework done. So it goes like this. Brief reading at the end of class last time and we just skipped over it. I was referring to the wrong thing. I'm realizing, guys, that the reading that you were to do that we skipped over was about the sizes of ions. Did you get a chance to touch on that? Oh, it wasn't there yet. Oh, it's fixed. So guys, basically it goes like this. Ready? This is the reading that you missed. So if you have a metal, and if it gives away, ready, this is stupid. If you've got a metal and if it gives away an electron, like sodium +1. So if you have a metal and it gives away an electron, will it get bigger or smaller? If you give away an electron, won't it get smaller? Right? And then if you have a chlorine atom and it takes in an electron, will that get bigger or smaller? Get the idea? Okay. So that is not the reading that I was referring to. Guys, this is actually the stuff that I was thinking that, that this is the reading we're going to skip today. You ready for this? So single bonds, all right, this is what this says in a nutshell. You're welcome to go over it if you want. But guys, if you got a single bond, a double bond, and a triple bond, which will be longer? Single, which will be stronger? Get it? Guys, that has a name. That is what is called bond enthalpy. Bond enthalpy is the amount of energy needed to break a bond. So triple bonds have higher bond energies and single bonds have lower bond energies because triple bonds are stronger than single bonds. Get it? Go ahead. No, and so what you're going to find out is that using this terminology that we've been sort of skirting around, a single bond is what we call a sigma bond. A double bond is a sigma and a pi bond, and a triple bond is a sigma and 2 pi bonds. And so what you're going to find out is that pi bonds are weaker than sigma bonds. The reason is because if you've got two atoms that are bonded together, that is a sigma bond, and then the double bond is a pi bond that's looping around. And because it's not directly in the bond axis, it's weaker than a sigma bond. So a double bond is stronger than a single bond, but it's not twice as strong because the pi bond is not the same strength as the sigma. Similarly, a triple bond is stronger than a double bond, but it's not 50% stronger because again, it's, yeah, you get the idea? Okay. Then guys, finally this. A little foreshadowing to where we're going to go next time. So guys, next time we're going to start talking about, and this is chapter 9, about the craziness that is the reality of Lewis dot structures. So guys, when you learned Lewis dot structures last year, you learned that we always have full octets. You learned that it's the S and P electrons that do the bonding. You learned that they like to be symmetrical. You learned all this stuff. And you're starting to get the sense that none of this is actually true. Well, guys, it gets worse in chapter 9. In chapter 9, we're going to talk, don't write any of this down, but guys, we're going to talk about some stuff. We're going to talk about molecules with an odd number of electrons. That's trouble, because if you've got an odd number of electrons, you can't have a full octet. So guys, why would a molecule want to form if it can't fulfill octets? The answer you're going to find out is reduced formal charges. We're going to talk next time. Then guys, we're going to talk about atoms that have more than an octet. Ready for this? How can molecules have atoms with more than an octet? The d electrons become valence. Oh yeah. And then guys, finally, we're going to talk about atoms that have less than a full octet, and this can happen when you've got simple central atoms, and it's actually easier for them to form single bonds with decreased formal charges than it is to create multiple bonds, because that causes stress. So guys, in the coming days as we get into chapter 9, we're going to talk about some of the weird. Guys, for now, all you've got to do is this. So, oh, I can't do that. This doesn't work for some reason. So guys, you are going to do your homework for the rest of the day. So guys, pretty straightforward homework assignment. The only thing that is you will be drawing all the resonance structures for these resonance stabilized molecules. Then guys, the KWL for chapter 9 is due next time as well. And that's where we are. So guys, the rest of the time is yours. We are going to work on homework. If you want headphones, you're welcome to do that, because now you're working on your stuff. But guys, we're going to get some homework done. So dig on in.